At 2:13 in the morning, one fan motor trips. In the first air handler, airflow falls to 0. In the second, one cell goes dark while the other modules keep running. That sounds like an easy win for the fan wall. But there is a catch: continuing to spin is not the same as still meeting the required airflow and pressure. So let us compare one large fan and a fan wall as two complete AHU systems. Both must be selected for the same design duty point, total airflow and static pressure at the same filter, coil, damper, plenum, and duct condition. If those conditions are different, the comparison is already invalid. Round 1 is resilience. One large fan is normally one air moving path, so a motor, drive, bearing, or impeller fault may stop that section. A fan wall divides the work among modules. If one module is isolated, the others may continue. But true N+1 capacity is proven only when the one module off array curve still reaches the required system duty point without exceeding speed, current, power, or sound limits. An unused square in the wall is not proof. Round 2 is part load energy. A single fan with a suitable variable speed drive can be very efficient. An EC fan array can run all available modules together, or stage modules and adjust the speed of those that remain active. Neither architecture automatically wins. Use the building's hourly load profile, the measured input power at each operating point, and the real control sequence. Annual energy is the area under that power versus time record, not a percentage printed beside a layout diagram. Round 3 is service. The single fan system has fewer motors, cables, controllers, and fault points. That simplicity matters when shutdowns are acceptable and a lifting route is available. Fan wall modules are smaller and can be replaced one at a time, which helps where access doors are narrow or downtime is expensive. The advantage exists only with safe isolation, guards, connectors, spare module strategy, and enough clearance to remove a cell. Round 4 is what happens across the coil. One large discharge may need a plenum or diffuser to avoid a concentrated velocity pattern. A well-spaced array can divide the flow across more of the coil face. Yet wall leakage, poor inlet clearance, recirculation around a stop cell, or a coil placed too close can destroy that benefit. Check the installed velocity map, do not award the point from geometry alone. Now acoustics. More small fans are not automatically quieter, because sound from multiple sources combines. Lower module speed may help at one operating point, while staging or high recovery speed may create another result. Compare octave band or declared sound data for the complete operating sequence, including the failure case. Finally, cost and controls. One large fan often means fewer power feeds, fewer communication nodes, and simpler commissioning. A fan wall adds modules, wiring, protection, control logic, and fault handling, but it can also reduce heavy lift service and add operational flexibility. Compare installed and lifecycle cost, not fan price alone. Here is the practical decision. For a simple comfort AHU with easy access, planned maintenance windows, and a tight first cost target, one large fan may be the better engineering answer. For a continuously operated AHU or CRAH, a constrained retrofit, or a process where reduced airflow is preferable to a full stop, a verified fan wall deserves the shortlist. Before purchase, request normal and one module off curves, absorbed power across the annual load points, sound data, control and failure sequences, electrical distribution, service clearances, and the actual AHU resistance calculation. A fan wall buys options. A single fan buys simplicity. The right choice is the one that meets the duty point through the operating events your facility actually faces. If you want a project-specific comparison, send the airflow, static pressure, AHU drawing, load profile, and required failure behavior. That is enough to begin a useful engineering review.